Now we take a look at some important property of the z-transform. So as we've seen before, here's the z-transform definition. We have the sum from n equals to 0 to infinity, our sequence, and this multiplication with z to the power of minus n. So the z-transform turns a sequence into a polynomial in z. So here we have a sequence 2, 4, 3, 1, and then we apply the z-transform, and we have this polynomial in z, so 2z to the power of 0, z to the power of minus 1, minus 2, and minus 3. A very important property of the z-transform is the shift property. So if we take two causal sequences, so causal means that n starts as n equals to 0, so we don't have negative indices, value z for negative indices. So if we have a sequence x of n and a sequence if x of n minus 1, which is the same sequence but delayed by one sample, and we take their z-transform, so this is the z-transform of the sequence x of n, here's the z-transform of the sequence x n minus 1, so we have these two results here, and if we use some index substitution of n mark is equal to n minus 1, or n mark plus 1 is equal to n, to get rid of this n minus 1 index in the transform. So we have now this here, and we see that this shows that a delay by one sample in the signal sequence, so in the time domain, corresponds to the multiplication with z to the power of minus 1 in the z domain. So we have here the z-transform, one signal, here's the delayed by one sample, and we have that it's in the z domain as a multiplication with z to the power of minus 1. So here's an example. If we have our signal, it's a sequence of 1, 2, 3, and we take the z-transform, so we have 1, 2 times z to the power of minus 1, 3 times plus 3 times z to the power of minus 2. If we delay this by one sample, so we insert a 0 here, then we will have this z-transform, and we see that we are multiplying this by z to the power of minus 1. So here, here, and we end up in here. So in the z domain, the delay shows up as a multiplication with z to the power of minus 1.